Billions of stars orbit around our galaxy like our Milky Way, but there's something that's keeping them from going far apart each other. Something mysterious, invisible, and strange. It's called dark matter. For decades, scientists have speculated that dark matter creates this sharp, dense core in the middle of our galaxies. But new simulations say otherwise. The life and death of stars, energy, supernova explosions have changed and shaped the fabric of dark matter, of what keeps galaxies together. In today's astrO episode, we'll be exploring this cosmological phenomena of how dark matter takes over our universe. And to guide us through this journey, we are joined with Professor Andrea Maccio, who is the Professor of Physics and Director of the Center of Astrophysics and Space Sciences, as you can see here, at New York University Abu Dhabi, and we're at the campus right now. And he explores large-scale cosmological simulations to understand more about dark energy, dark matter, and galaxy evolution, and how invisible can see how it changes our universe. So welcome, Professor Andrea. How do you feel today being here on the astrO podcast?
Well, first of all, thank you for having me in your podcast. I'm super happy. I'm happy we're here at NYU Abu Dhabi together to discuss dark matter, maybe about a bit of dark energy later on, and structure formation. Very happy to be here, very happy to be with you.
It's an honor to have you here. So I have a lot of questions today that we must dive into, and I'm very excited for our cognitively stimulating conversation. So first, I want to talk a little bit about dark matter and dark energy, but that sounds very, very broad. So could you maybe give us a small definition of what dark matter and dark energy is?
Sure. Let's start with dark matter, which is maybe slightly easier to describe and understand. As you were mentioning, stars are going around the galaxy, and there is a very simple relation between the velocity which stars go around and the mass of the object they go around. That's, for example, is how we know the mass of the sun. We know the mass of the sun because we know how fast the Earth is going around the sun. And if you measure the velocity which stars go around the galaxy, you can measure the mass of the galaxy. This was done already 70 years ago by Vera Rubin and others, and they realized immediately that the mass you get is very, very different, very much larger than the mass you get by summing the mass of all stars and even gas in a galaxy. There's this missing mass. And it's missing in the sense that it doesn't emit any electromagnetic radiation, and that's why we dub it dark matter, right? It's matter, it's there because we know the gravitational effect, but it doesn't emit light. That's where we were about, as I say, 70 years ago, the beginning. And unfortunately, I have to say, we are still there. We still call it dark matter, and as we will, I assume, talk about during this podcast, we don't have a very great idea what dark matter is.
But we have found a lot of candidates for its particles, like WIMPs, weakly interacting massive particles. And I know that in CERN we've been trying to smash a lot of particles together to find different types of particles. But then for dark matter, it's it can be too dense, it can be sometimes too light. So, there's a lot of research going on about that as well.
Correct. There is, as soon as you have a mystery in the universe, we physicists, we like to understand how things work. So the first thing we do if there's a mystery is try to find a solution, right? We are like space detectives, if you wish. And the way we go around problems is by running experiments, as you were mentioning. And there are a lot of experiments that are run through the world, both at CERN. There is also a lot of underground experiments in Italy at the Gran Sasso laboratories, now in some mines in Canada. And the idea is always that if dark matter is in the universe, there must be some dark matter around us. And hence this dark matter, even though it doesn't really talk or interact with ordinary matter, now and then, one of those dark matter particles will hit a normal nucleus and we release some energy. That's what we are trying to look at.
I see.
Unfortunately, we have to say that all the experiments that are run now, especially the underground ones, they have given no results, in the sense they've told us what dark matter cannot be, because if it was something else, we would have seen it. But they have not had what we call a detection, a signal that tells us, oh, this is dark matter. Similarly, CERN has run several experiments, and what CERN was hoping to find was some missing mass, in the sense that when you smash two particles, a lot of other particles are produced. There is a gigantic detector around the point of collision. One example is ATLAS. And they were hoping that something would be missing. The same way that we are missing matter in the center of a galaxy, they were hoping some matter could be missed in this collision. And then also in this case, unfortunately, we have a known result in the sense that everything is accounted for. I mean, there was a missing mass, that was the Higgs boson, which is a great discovery, Nobel Prize awarded, but there was no sign of any new physics beyond what we already know. So that's why at the moment the search for dark matter is a bit stalled, in the sense that yes, we have a lot of candidates, but none of them has given us a positive result. I mean, like a detective story, we're still inspecting, we're still thinking, scratching our heads, and so I think we will soonish find something. I was more optimistic a few years ago with CERN and the Grand Sasso laboratories, and now unfortunately it's not giving us the results we wanted. But on the other hand, having a mystery is good, right? It pushes you to do more research, and so in a sense, solving a mystery is satisfying, but it's also the end of the road, where we still have a lot of road ahead of us.
And always when we look for while we look on the search for dark matter, we might find new things that we maybe didn't know about before as well.
Absolutely. Serendipity discoveries are always there, and sometimes are the most interesting ones. So yes, we should keep looking, and any day we can have something we don't understand. Physics at the end proceeds by unknowns, right? When there is something we cannot explain, that's when we move our science. So that's what happened, for example, with general relativity, the period of Mercury. That's what happened with quantum mechanics, the photoelectric effect. So having data points we cannot explain what pushes us forward. So in a sense, mysteries are good. I
totally agree with that. So finally, since dark matter and dark energy we know take up almost 95% of our universe, what are the leading theories about their physical nature, or how do they influence our cosmological structure and formation?
Yes, maybe I can say a few words about dark energy before.
Yeah, of course,
dark energy, we know it's there because our universe is accelerating. And now, in a very simple way, if you accelerate a system, you need to provide energy. And so this energy must be somewhere, and very similar to dark matter, since we don't see it, so no emission, the electromagnetic spectrum, we put this dark in front of it, which sometimes is just a proof of our ignorance. When you call it something dark, it means that you don't have a great idea what it is. And so that's how we know dark energy is there, by studying how galaxies are moving and how our universe is expanding. That was also a Nobel Prize awarded in late 90s. 1999 was the discovery of dark energy. We have, for dark energy, dark matter, it's a bit peculiar because it's a bit strange. We don't know what they are, but we know very well how do they influence our universe, which is strange if you think about that, right? You have an unknown substance, but you know very well what it's doing. So we know that dark matter is keeping exerts gravitational force, so it's an attractive force, keeps our galaxies together, slows down the expansion of the universe. Dark energy is doing more or less the opposite. It's powering the accelerated expansion of the universe, and so is drifting galaxies away one from each other. So they have opposite effects, they're both acting. They have roughly the same strength in the current universe. That was much different in the past. And current theories tell us that dark energy will dominate the future of the universe. So the universe most likely will continue to expand, and galaxies will be so far away from each other at a given point they become disconnected from each other.
I see. And I know dark energy is very responsible for the expansion and acceleration of our universe, but I think I had read somewhere that there were two scientists who had created this microwave detector, and they thought nothing of it. They were kept receiving this really strange signal, and then finally I think they got this microwave in the detector, and that was kind of proof of the expansion of our universe, which showed that from the Big Bang, well, it kind of also contributed to the theory of the Big Bang, because it showed that after that explosion, lots of types of electromagnetic waves finally stretched out and then finally became into a microwave. So that was one of the discoveries, that there's something that's accelerating our universe as well.
Yes, I mean, we are talking about so many Nobel Prizes now at the moment. You're referring to Pence and Wilson.
Yes,
they
exactly.
were two technicians, think of Bell Telecom, And what they built an antenna. What they found out, there was this sort of noise, this background noise in their antenna. And what they found puzzling was that this background noise that they thought could be another radio station somewhere was the same in every direction, right? And when you have something which is the same in every direction when you point to the sky, it usually means it cannot have a Earth origin, right? It should be astro outside the Earth, most likely astrogalactic. And now the joke I always tell my students is that since they were engineers, when they have questions, they call up a physicist, right? So they call up a physicist, especially Bethe, and they together they understood that what they have stumbled upon was the radiation from the Big Bang. In the sense this radiation was emitted at the time of the Big Bang, and then has permeated the whole universe. And of course, since the universe is expanding, like when you expand the gas, the temperature of this radiation is going down, and nowadays around 2.7 Kelvin, right, where the 0 Kelvin is the absolute zero, minus 270 something degrees.
But since your research relies a lot on cosmological and numerical simulations, could you explain how these simulations help you model the role of dark matter in large-scale evolutions of the universe?
Yeah, absolutely. If we go back about 550 years, we go back to Galileo Galilei. And Galileo Galilei was the one who told us about the scientific method. He told us if you have a theory, you have to devise an experiment to prove your theory. And this is the foundation of modern science. If you think about that, in the good old times, people were sitting around a fire and just discuss about the universe. I think the universe is made of 4 elements, 5 elements. They were not running experiments. The only thing they were doing was to use their intellect to think about stuff. And Galileo was very clear, right, that that's not enough. You need to build an experiment, which is great, but becomes a little difficult when you have to do with galaxies and the universe, right, to build experiments. So it would be very hard to recreate in the lab the condition of the Big Bang or the evolution of a galaxy that involves temperature, densities, and timescale, which are way far, way beyond our reach. So what we do in my group and many other groups around the world, we run numerical experiments in a computer. So the idea is the following. You have some assumptions about how the laws that govern the universe. You have some assumption about the ingredients of the universe. And you put everything together and then you run a computer simulation of what you're doing. The parallelism I always use is that it's very similar to baking a cake. If you want to bake a cake, you need the ingredients, you need the recipe, you need an oven. So let's imagine that somebody brings you a very nice cake, right? You want to try to recreate it. So the first thing you have to do is to find out what are the ingredients, right? There could be some ingredients are more important than others, right? Some are in a larger quantity. But once you have the ingredients, then you need to get the recipe. So in our case, the ingredients are dark matter, dark energy, and initially you only have gas in the universe. So you put these 3 things into your cake simulation. Then the second ingredient is the recipe, right? That's maybe one of the hardest, right? Because even if some ingredients could be clear, how you mix them changes completely your cake. So in our case, the recipe is how you mix those ingredients together. And so it has to do, for example, with the laws of general relativity. For gas, you have the law of the gas, PV equal NKT, the typical law of ideal gas. But gas also, there is absorption and emission of energy. Then you have star formation, supernova explosion, black holes. So what we do, we think we have some understanding of those laws. We put everything together. And once you have the ingredients and the law, you put in the oven. The oven for us is a supercomputer. And you ask the computer, please evolve the system. That's not far away from what people do with the weather forecast, right? You have the incoming cold flow, hot flow, you put in a computer, that's what you usually see on TV, right? When they tell you how the kind of cold front is going to move, evolve, those are computer simulations. I will do something similar. And so at the end of the game is that at the end of the simulation, you have some virtual galaxies, and then what you do, you compare them with the real ones. Right. And so if they look like the real ones, then you know you're on the good track, right? You know that either the ingredients, the recipe of their mix is the correct one. If you get galaxies that do not resemble the one in the universe, you know something went wrong. So I always tell my students, if you get a galaxy which is squared, we know there are no square galaxies in the universe, so you know something is wrong.
Right.
And so the goal now is to make your recipe and the amount of ingredients, how you mix them, more and more precise. And that can only be done with computer simulations.
But do you recreate, like for simulations, do you recreate events that have already happened in our universe, or are you trying to predict that something that could happen?
So it's slightly more complicated than that. And so we don't recreate the universe, we create a universe. Right? Here English is a very good language for that. The universe, a universe. In the sense that we know how the initial condition of the universe, but we only have information on, we're missing some information on those initial conditions. In the sense that, let's suppose you have a wave, we know everything about the intensity of the wave, we don't know anything about the phase of the wave. So there are some information that we cannot access. It's like if you, for example, let me see, if you draw a dice, right, you draw it 200 times, you get the distribution of numbers. And you know that on average, you will get every number the same amount of numbers, right, from 1 to 6. Now, I do the experiment 1,000 times, you do the experiment 1,000 times. Statistically, we're going to get the same distribution. Every number, let's suppose we do 600 times each. Every number comes around about 100 times. But most likely we never get the same numbers, exact same, right? Maybe for me number 6 came 105 times, for you 98. So statistically we have run the same experiment, but they are not exactly the same experiment. And that's the same we do in numerical simulation. We create a universe which statistically is the same as our universe, but it's not exactly the same. So going back into the past, we get the universe that it's similar to our universe, I don't know, 3 gigayears ago, but will never be our universe 3 gigayears ago. We usually, since we compare, that's about the first question, so we don't reproduce events that happened in the past one by one, but statistically. About your question where we go evolve in the future, we do that for a few cases. For example, there's a very interesting, something that will happen in about 5 billion years, 5 gigayears between us and our neighboring galaxy, Andromeda. But since we want to compare with data, we rather prefer to stop at today, right? Because up to today we have data we can compare with. Going into the future, it doesn't have any data to compare with, so we try not to do that.
I see, but do you think that, I mean, there are, like, as you said, like one of the cases of the merge of our galaxy and the Andromeda galaxy, obviously hundreds of thousands of scientists across the world, they create theories on these kinds of situations. And do you think numerical simulations or the simulations that you create could help them like see their theory in maybe, because they might have a different outcome of what might happen in a merger. Some other scientists could have a different outcome of the merger. So do you think they could like visualize these and put them into the simulation, and then they could like compare it with each other and then look for a new solution?
Absolutely, that's what we do. So numerical simulation are the experiment, the only experiment you can run when it comes to the universe. And so by combining theories with numerical simulation, we can prove them either wrong or right. But it's more complicated than that. So we always thought that Andromeda and the Milky Way, they're going to collide in 5 years. Very recently, a group has provided a new set of simulations where they have the Milky Way and Andromeda, but for the first time they also include the two big satellites galaxies of our own galaxy. They're called the Magellanic Clouds. There's a large Magellanic Cloud, the small Magellanic Cloud. They're only visible from the southern hemisphere, and I've never been there, but people told me they look like clouds in the night. They're very bright. Fun fact, they found out that in some configurations of their simulations, Milky Way and Andromeda will not merge, will pass by without colliding. And that has to do with the position of the Large Magellanic Cloud, LMC, and Small Magellanic Cloud, SMC. And also very interesting, since we don't know the exact motion of those galaxies in the sky, because as you might know, we for objects that are far away, we only have the velocity along the line of sight. So we can tell if an object is moving towards us or away from us, but the transversal velocity, so if this object is going right or left in the sky, isn't very hard to measure. And so given these unknown on the motion of the large and the small Magellanic Cloud, they concluded that there's a chance, about 20%, that Milky Way and Andromeda will not collide. That's new, that's not my own simulations, and I'm thinking whether I want to try to see if my simulation give the same results, but tells you about the power of simulation, something that we give for granted. When you add more information, there is a chance that we will not collide.
I think the mergers of galaxies really depend on the other neighboring galaxies as well, since the gravitational field is they're all, because our local group has couple of few galaxies, and even if Andromeda or our Milky Way don't collide, there could be a chance that it could collide with other galaxies over time though.
Well, collisions in the sky are frequent. So galaxies tend to collide. If you look at any galaxy which is very massive today, they all had at least one major collision throughout their life. The time scale at which it happens and the probability of this to happen is very high, but it's never 100%. So Milky Way, for example, it's likely that the Large Magellanic Cloud at a given point will go inside our own galaxy. The time scale it might be extremely long. And the same from Milky Way and Andromeda, they will pass by each other, there will be some tidal deformation, but whether this is a head-to-head collision, that seems to be, there are people that are questioning this. As I said, if I remember correctly, it's about 20% of the times they did not collide, 80% of the time they still did collide.
I see.
But as I say, collisions in the universe are very common, and every galaxy which is very massive today, especially galaxies that are elliptical in shape, they all had at least one major collision through their life.
I mean, I've seen lots of simulations of them colliding, and they seem really nice because it's like a very cosmological dance, like they're dancing
Absolutely,
together.
yes. They meet,
together.
they go far away. It's like courting, right?
Right, exactly. So it's very
beautiful.
beautiful.
Like dating.
So I want to go a little bit into galaxy formation and the dark matter halo that surrounds it. So how do dark matter halos actually shape and form the evolution of galaxies, and what have simulations revealed about their internal structure and its dynamics? Because I think another evidence that dark matter is actually there is how galaxies are actually spinning. We've been seeing their disks spinning for a long time, but we had no explanation for it. And then finally, scientists were like, okay, that might be dark matter. So just want to know your opinion on that.
Yes, I mean, every galaxy is a sort of matryoshka, those Russian dolls. So at the center you have the stars, a little bit farther out you tend to have more gas, but then on large distances, so on distances which are maybe 5 to 10 times the size of the disk, that's what you usually see in a disk galaxy, the dominant force is dark matter. The theory we have in its basic formulation is that first you form this, let's say, balls, halos of dark matter, and they then work as gravitational attractor. So what happened, the gas which is around the universe falls into those dark matter halos. And now gas has the possibility to lose part of its energy, right? When the gas is falling in, it's going to emit some radiation, and then it's going to reduce his total energy so it can settle at the bottom of this potential well. And then what you have is then when the gas gets very dense and also very cold because it's losing a lot of energy, it will start to form stars. So that's why you have the dark matter, the gas, and the stars in the very center, this sort of cosmic matryoshka. Dark matter halos shape, it's in principle easy to calculate because dark matter only feels gravity. And so it's very easy to do simulation with gravity. And so in late 90s, there were a famous paper that told us that all dark matter halos, they all have the same shape. And this is very interesting. That doesn't mean if the dark matter halo has a mass of 10 to the 14, so 1 with 14 zeros, the mass of the sun, or 10 to the 10, 12, 8, 9, 6. It's always the same shape. Now, what is interesting that this sort of universal shape, it's good to explain some objects like massive galaxy clusters. Those are objects that are made by 1,000 galaxies. But when you go to dwarf galaxies, those are galaxies that have maybe 1% of the mass of our own Milky Way, there seems to be some issues. There seems that this universal dark matter halo was not fitting the data. And many people work on that. My group has been very at the forefront of this kind of research, and we have realized that, wait a second, the dark matter halo is forming a way, but then the dark matter halo doesn't live in a universe without stars and gas, right? There is, as you mentioned, right, supernova explosion, the gas moves in and out. And every time you move gas and stars, you are changing the gravitational potential. You are changing the way gravity is felt by dark matter. And dark matter has to react, right? And we found out with other groups that dark matter reacts differently in different objects. That can explain why all dark matter halos were created equal in a sense, but during their life, they start to have different shapes and different, especially the central concentration is different. That helps to explain some of the observations that are seen. And interestingly, of course, all of that, it only comes from numerical simulations, because again, it's very hard to do paper and pen calculation in the system. They are what they call chaotic systems, and they're also extremely non-linear systems, meaning that a numerical simulation are maybe the best and only tool you have to solve these issues. And of course, we as simulators, we take a huge advantage of the progress that computing has done in the last years, right? When I started, I think the computer I used for my master thesis had less power than my mobile now, right? My phone has more computational power than the computer I used in the 1998 to do my master thesis. So we gain a lot by that. So that's why we can push our knowledge forward.
And I think in the beginning when you were talking about how, I mean, I was also researching, I was also looking into your paper where you and your group were using, you and your collaborators were using the NIHAO simulations, where in the beginning we know that there's first dark matter halos and then the gas and stars start to form. But then in your paper, I think you guys found that the baryonic physics, which is more of like the stars, the gases, the feedback, actually affect the dark matter's density in these galaxies. So I did have a few questions about that from your paper. So my first question, that before we thought that there's a universal like dark matter profile for all galaxies, but that no longer applies anymore. So does that mean that every galaxy has a unique type of density profile, or is it all the same? I mean, many galaxies are formed by mergers, some are born. So I guess what could be the
Yes, thank you. And by the way, you mentioned our simulation. You say NIHAO, but that means ni hao. Ni hao is a salutation, and it's an acronym. It's a salutation in Chinese, means hello, and stands for numerical investigation of 100 astrophysical objects. So we are very proud of our ni hao simulation, which we have done in collaboration with some colleagues in China.
I see.
Yeah. By the way, recently we started a new project, and instead of calling ni hao, we call it hello, and it stands for a high redshift evolution of large and luminous objects.
Wow.
So we are using salutations. We tried to put into this program salam, but we couldn't find a good definition of the acronym. So I'm happy to suggestions. Maybe some of the people listening to your podcast can give us a spelling of salam that might be related. S could be simulations.
Yes.
But the M could be mass. I don't know. We're very, very looking forward to some help from the people that will listen to this podcast. Yes, as we were discussing, dark matter, if you only include gravity, all dark matter halos are the same. But as I mentioned, when you form a galaxy, there's more than just gravity, right? The simple fact that we form stars, the simple fact that we see stars, tell us that there is more forces at work. Now, even though, for example, when you have a supernova explosion, there's a huge amount of energy is put into the universe, this energy does not couple, we say, with dark matter. So dark matter is transparent to this energy, because dark matter doesn't interact with photons, with electromagnetic radiation. But this energy is pushing the gas, right? The gas is going to explode. And so when you move the gas, you are changing the gravitational potential. And so dark matter has to react to that. So what we have, the idea we are putting forward, and has been followed up by other researchers, is that since every galaxy has its own history of formation, as you mentioned, some have major mergers, so big encounters, some other they have only small encounters, some have a very active life at the beginning, right? They form older stars at the beginning, some others maybe they have a more gentle evolution. If you think about that, it's like the growing of kids, right? Some kids, they always grow in the same way, but if you take two kids of the same age, the same grade, they might be very different in height, right? My boy, he's 13, is almost 180, right? He's the tallest in his class. And so the growth, even though at a given point when they become adults, they will have roughly the same height, especially in middle school, that there's huge differences. And hence the same for galaxies. Even if at the end they might have similar stellar masses, which is the height in my comparison with people, they might reach this final point in very different ways. And so we will have very different distribution of dark matter in their inside. Of course, dark matter as a global is 80% of the mass of a galaxy, right? So you can move gas around, but it's still a minor perturbation. So you're not going to change dramatically the distribution of dark matter. But as I was mentioning in the beginning, galaxies are like matryoshkas. So in their central part, they're not dominated by dark matter. In the central part, they might be dominated by stars and gas. So for example, at the solar neighborhood, so the distance we have from the center of the galaxy, which is give or take 7 kiloparsec. A parsec is roughly 3 light years, and kilo means 1,000. Right. So we are in a region where we are 50-50 between dark matter and ordinary matter. So in the center, clearly this movement of gas can really perturb dark matter. So the theory we put forward is that there is a specific set of galaxies that will have the maximum perturbation in dark matter.
I see.
And this seems to fit very well with observational data, which always it's the goal at the end, right? You can have all the theories you want, but if you don't fit data. That's been one of the success of NIHAO and other simulations around that. We can reproduce what is called the rotation curve. So we can reproduce how the velocity at which stars rotate around the center, which of course depends on how is dark matter distributed.
But a question that came into my mind while you were explaining was that while galaxies grow older, and does dark matter start to deteriorate at any point of time?
Well, current theories say that dark matter will not deteriorate. Dark matter will always be there. So what we know, in a sort, by looking at the universe, is that the lifetime of dark matter particle is as long as the life of the universe, because they've always been there. So we don't expect them to decay or, as you mentioned, deteriorate. So the amount of dark matter within a galaxy is sort of a constant number.
I see. Okay, that's pretty interesting. And I also know that you work a lot into black holes as well, and I'm also a very big fan of black holes. And we speculate that there are black holes in the middle of every single galaxy. And but my question is more of what actually happened a bit recently, I think a few months ago, where 2 black holes, extremely massive, were in a binary system, which is basically when 2 black holes or 2 bodies orbit around each other. And they weren't supposed to merge, and I think the headlines called it a forbidden black hole. And they did. I mean, I don't know if you know anything about what had happened, but so they weren't supposed to collide, but then they did, which proved a bunch of the physicists who's had tested them on simulations said that they were never going to merge, but they actually ended up merging. So do you know maybe why that might have happened?
Yeah, maybe we should clarify a few things, because there are 2 kinds of black holes in galaxies. One is the black hole at the center of the galaxy that usually we call supermassive black holes. And those black holes, just to give you an order, an idea, they have a mass of about 1 million suns, 1 million and above. We also have black holes with 100 millions of sun masses. They form from the beginning of the universe. We don't really know. We don't have, say, a single theory about their formation pattern. And then they grow through the whole history of the galaxy by accreting more and more mass, and they become these gigantic beasts at the end. Then there are the other kind of black holes, which are the stellar black holes. Those black holes, they form from a dying star. Through the recent years, we have measured a thing which is called gravitational waves. So what happens when massive objects start to dance around each other, could be 2 black holes or a black hole and another very compact object called neutron stars, they perturb the fabric of the space-time. And the same way when you throw a pebble into a pond and you create ripples in the water, those dancing objects, they create ripples in the space-time, and those can be measured through gravitational waves. And we have now the LIGO and other experiments here on the Earth that are measuring these black holes, and now we have a planned experiment called LISA, where we're trying to measure black holes from space. This is going to be 3 spacecrafts that are going to touch it. It's a crazy experiment. And those are the ones we are measuring right now. That's the ones you're referring to. One thing we have found out in recent years, which is very puzzling, is that we didn't know those very massive black holes would exist. We had the idea that maybe 10 solar masses was kind of the limit that those black holes can reach. And instead, we have found several proofs of black holes around 30, 60, almost 100 solar masses. Of course, those numbers come with some errors from measurements, so we don't know them very precisely, but there is a clear indication that very massive black holes exist. And when they dance, you can imagine they create gigantic ripples. But those are still black holes with a mass up to 100 solar masses. The one in the center of the galaxies, they have masses up to 100 million solar masses, so much larger. Those ones, seeing them merging, it would be an extremely rare effect. LISA, this antenna that will be in space, might give us some ideas. So for the moment, I think the idea of this dancing black holes is limited at the stellar mass black holes. And about the paper you were referring, I think it's very interesting, and it tells you that sometimes nature is more complicated than what we expect. Sometimes we think some things are forbidden, but nature somehow always find a way to make them happen. And that's, as I was mentioning before, is very interesting, because then you have a mystery, and trying to solve the mystery will push our knowledge forward.
I see. And a little bit more about like your work and what you do with black holes is that in your studies of massive galaxies and their supermassive black holes, how do mergers and feedback processes affect the co-evolution of black holes or maybe the galaxies over time?
Yes, as you mentioned at the beginning very correctly, we think there is one of the supermassive black holes at the center of every galaxy. And as I mentioned, those black holes are huge, right? 100 solar mass, 100 billions, 100 millions of solar masses, 10 to the 8. We have immediately realized about 20 years ago, as soon as the proof of this black hole at the center of galaxies were there, that those black holes, they should have or might have a strong influence on the evolution of the galaxy. And how they do that is not through their gravitational force. Sometimes people think naively, oh, you have such a big object, it's going to have a gigantic gravitational pull. But if you think about that, the mass that you have in the center of the galaxies is 100 up to 10,000 times more than the black hole mass. So the black hole is massive, but not that massive. So what we think is happening is that these black holes are eating a lot of material, mainly gas. And when the gas goes into the black hole, it gets accelerated very close to the speed of light. And at that point, it emits a lot of energy. So the energy is not coming out from the black hole, but from the material which is falling into the black hole. This energy has a huge impact on the galaxy, because practically what you have is like having a big source of energy, like a gigantic lamp at the center of this galaxy. And what this lamp does, it pushes away the gas, it gives energy to the gas gets hotter and expands. And so we have realized, again, something like 20 years ago, that those black holes are the responsible of why some galaxies have stopped making stars. Practically, some galaxies, I'm going back to my analogy with kids, some galaxies have stopped growing completely, right? They don't produce any stars. Just to give you an idea, our own Milky Way produces 1 to 5 new stars of the mass of the sun every year. So every year there are 5 new stars born. Galaxies that are at the peak of their star formation, so they're growing very fast, they can easily produce hundreds or even thousands of stars per year. That usually happens during mergers, when you smash two galaxies. But some galaxies, they're not producing stars. And that's puzzling, because there's a lot of gas around. Why they're not growing? Maybe a little bit, but they should be growing. And now what we think is that the black hole in the center is putting so much energy into the galaxy that is preventing this star formation. So that's something that now I think is commonly accepted by most of the community. And so there is this idea that the black hole and the galaxy, they are growing together. And that's why we talk about coevolution. And it's interesting that there are several ways to try to prove it. And lately we have used some machine learning technique, which is called causality, in order to try to prove that there is a causal connection, right? Sometimes you have a correlation between two quantities, and you have no actual causation. There's a very nice example, is that If you plot the number of ice cream that people are eating and the number of sunburns people are having, they are correlated. Right? So you can tell, okay, if I want to stop people to get sunburns, maybe I should just prevent selling ice creams. But we both know this is not the case, right? What happens that when it's hot, people eat more ice cream, and of course they go to the beach and they tend to get sunburns, right? So there is a correlation between the amount of ice cream which is consumed and the amount and the number of sunburns, but there is no causation. It's not that it's the ice cream which is causing the sunburns, and it's not that you get the sunburn and you eat an ice cream to ease your pain, right? So it could be that sometimes you have a correlation between quantities but not causation. And this new branch of machine learning called Causality can help you to understand what's going on. And we have recently a couple of papers which have been accepted and also quite famous machine learning conferences and computer science conferences. And we're trying to push this idea of causality into astrophysics.
So you use that a lot in your numerical simulations as well?
Correct. So we apply these techniques to our numerical simulations to show that you can understand if there is a causal link or just correlation. Correct.
Right. And also, going back to the galaxies that stop producing stars, would it be better for a galaxy who doesn't produce stars to merge with one that does produce stars, and then, it would be back to a very normal galaxy that produces a lot and then grows very rapidly?
You are spot on. It's amazing. This process is called rejuvenation. It has been seen, and it's when an old galaxy gets a merger with a new galaxy. The new galaxy is gas rich, and suddenly what you start to form new stars. And now if you look at the end of the process, these galaxies will have like two populations of stars, an old one, a young one, and nothing in between. And that's how we know that happened. Right? It's like having a village which only have people above 60 and below 10, right? Somehow you know that those ones cannot be the parents of those other ones, and so there must be a population that you're missing. And this is called rejuvenation, and it's seen in several galaxies, yes.
And coming back to when you had said that when black holes start feeding and accreting on mass of a galaxy, it has immense amount of energy. And I remember reading about this black hole that were producing jets, which is like when there's a huge amount of energy, they start to produce jets. And then you said it's not from the black hole, but it's actually from the materials that are around it. But I think the jet was so huge it exceeded the cosmic web, which is basically like the web of galaxies. And then if you look at it from a very like bird's eye perspective, then you can see like a full web of it. But it was a very humongous jet, and it was something that we didn't think would ever happen, actually.
Yeah, well, the point I wanted to make, you are absolutely right, and I'm always amazed by your knowledge of astrophysics. The point I wanted to make is that it's not the black hole itself putting out this energy. Even the jet is created by so when material falls onto a black hole, it's tend to form first a disk, and then you have from the material falling in, you have this very gigantic jet. And it's a jet because you have a lot of general relativity effects that do this collimation, so that's why the energy doesn't come out as an explosion, but as a jet. And those jets are predicted by general relativity. There is a lot of people here at NYU AD studying them. And the properties of these jets are, as you say, very, very, very amazing. And there are jets, as you mentioned, that extend beyond the galaxy. So you have the galaxy and you see the jets that maybe can extend up to 5 or 6 times outside the galaxy. And they're not very common, the super powerful jets, but we know they do happen. And they are one way in which the black hole is somehow injecting energy into the galaxy. And they're crazy beautiful, and some of them are nearby. Those jets are studied intensively, and they are one of the, I think they are the most powerful energy source in the universe.
Right. And I mean, I'm very intrigued by the phenomena of black holes, and I've been looking into more of the theoretical side where the information that gets stored in black holes, and like, do they get lost, like where does it go? So I really like looking into those kind of things, and then these huge cosmological phenomena that there's huge amounts of energy coming out of them. But I think this discussion has been very, very insightful for me, and I think it's also to know that we have much more coming ahead. As you know, something that surprises me is that back in the 1800s, 1600s, when scientists and physicists didn't have any kind of like technology or any kind of like known of like what's happening outside, they still created all of these laws that we use and apply today. Like Isaac Newton wanted to understand elliptical orbits, so he created a whole type of mathematics called calculus for that. So I think with us, where we have so much technology around us, we can achieve so much more.
Absolutely. I think the limit is the sky, and we're also developing new mathematics to understand black holes. So you mentioned the loss of information. We have colleagues here in NYU Abu Dhabi that work exactly on that. And they work with mathematics that I have troubles to understand, right? And forget about calculus. We are getting very, very deep into a field which is high energy astrophysics and string theory. But yes, the limit is the sky, and I think at the end we are powered by those mysteries, as we were saying in the beginning, and so having them will push us forward.
Right. And one last question that I want to ask is not about, it's like more of your background. Like, why did you get into astrophysics, and what inspired you, and what like maybe advice you could give to, you know, young astrophysicists who want to pursue it in the future like me?
Yeah, I'm a very peculiar astrophysicist in the sense that I never had a telescope in my life. I know nothing about the night sky. If you bring me to the desert, which is very common here in Abu Dhabi, I'm useless. I can tell you about the evolution of stars, I can tell you about the evolution of black holes, I can talk about dark matter, dark energy, but if you ask me about constellations or which planet is where, I'm completely useless, which always comes as a huge surprise. My friends know about that, and they tease me on this. What pushed me forward is I like to understand how things work, both mechanical things, but also big things. For example, I remember one of the first things I asked myself is why there are seasons. And the answer I gave to myself as a little kid was, oh, we must be closer to the sun and farther away from the sun. And then I remember once I was looking at TV, and there was the Rio Carnival. And in Rio, it was February, it was Carnival, and everybody was dressed like summer. And I asked my father, I said, yes, when here's winter, in the other hemisphere is summer, said my father. And I said, well, then my theory is completely wrong, right? It cannot be distance. And of course, I learned about the axis and the inclination of the axis of the Earth and Kona. So for me, the turning point was around the age of 15, 16, when I was gifted the book, which was A Brief History of Time by Stephen Hawking, Dal Big Bang ai buchi neri in Italian. And I remember I read that book, and if you look, I've said that in a few other interviews, and I think I understood 30% of it. I don't know if you ever read it. It's very dense, very compact. And then I found it so fascinating, and I said, I really would like to understand more of this. And I started asking around my parents. My father's a lawyer, so he didn't know much about science, but I said, well, I think you need to study physics. And then I realized I like math, and so for me, theoretical physics and then cosmology, astrophysics was the right path. So I don't come from camping outside, watching in the stars, having a telescope, which is wonderful, by the way, right?
Yeah,
I always get amazed when we go out in the desert with our students. I always am, but I'm as amazed as they are, right? I should be,
of course.
I should know better, but I'm always very surprised by the night sky. And then I studied physics. I love, as I mentioned, I really like math, and then my path was set. So I knew I wanted to be, well, I was hoping to be a professor since I was the age of 16, 17. That's what I wanted. I wanted to do research. It was very clear to me. And then I went through the usual stages. I did my university degree, then I got the PhD in astrophysics, then I started moving around the world. I was in Switzerland before, then I became a professor in Germany. And then in 2015, I was offered a position here, and I thought, oh, this is great. It's a new university, it's growing, there's going to be a lot of momentum, a lot of things to be done. And I was very happy to join. And through the years, we created the Center for Astrophysics. Now we have a new PhD in astrophysics. I'm very happy. The advice I want to do with young people is that do something that you like, because this is maybe the most important thing. Try to do something useful, try to have a long-term plan, but try to do something you like. And enjoy the moment, right? Don't think too much ahead. If you like math, study math. If you don't like math, go somewhere other direction. Try to do something that you are passionate about, and that will make your life easier, right? You never know where you're going to end up, because if you told me, I don't know, 35 years ago, that would be in Abu Dhabi today. First thing I would ask you is, where? I had no idea where Abu Dhabi was. And second, I would never thought about that. I was seeing myself in the US, maybe in Europe, but not here. Now I love Abu Dhabi, I love the UAE, I love NYU Abu Dhabi. So I'm very happy. So it's very hard to predict where you end up. So don't think too much about that. Do something that you like, and life would be open for you.
Well, that's amazing. I really liked hearing about your journey, and also my interest also started from just a book. I mean, I wasn't very looking at the night sky is obviously a very, very beautiful thing, and I like seeing the things that I'm studying about is actually happening up in that sky. So it's very interesting. But thank you very much for joining us on the podcast. It was an honor having you, and I hope that we could have you again.
Absolutely.
And thank you very much.
Thank you, and it's been a pleasure chatting with you. Thank you very much.